Here we go. Welcome back, gentlemen and ladies. Welcome, everyone. This is Couch of Science. And after a long pause, we decided to come back with a special event. And today, with this special event about bioengineering science, to help me to introduce you this topic and our guest, there is Mikhail. Hi, Mikhail. How are
Hi,
you?
Michele. You good?
Yes, good. How was your summer? Even though it's a very
Pretty
weird
warm.
summer. Pretty warm. Oh, okay, yeah. It definitely was very, very warm here in Brussels. That was insane, really. Oh my God. Now it's a kind of better, even though still it's warm. But okay, so first of all, Mikhail, what we are going to talk about today? Before we start with your introduction, let's talk
Definitely.
about a bit of.
Today we're talking about the future of science, of biology, how to create organs with machines. It's going to be pretty impressive.
Yeah, it's going to be very impressive. So for everybody that is here with us, welcome. And if it's the first time that you are here with us, the format is very simple. So we invited a guest that is going to talk about a topic that, as Mikhail was just saying, it's about printing organs in a very vulgar way to say, let's say. But if you want to interact with us, please just write in the comments. Even though if you are following us on YouTube or Facebook, just write in the comment. And if you have questions, if you want just to say hi, if you want to say that is warm also here, I don't know, whatever you want, just write in the comments. And after the presentation of our guest, that for now I'm not going to disclose who he is, we are going to have a small Q&A session. So if you have any questions also for him regarding the topic, just let us know in the comments and you will be able to have a reply probably very in live session. So first of all, so we are talking about printing and what actually is the most hot topic about printing is 3D printing and 3D printers that in the latest year they're become cheaper, easier to use and to install. Everybody has one at home in a certain way, or at least everybody that wants to hack a bit the system, they have one for million different purpose. But Mikhail, you prepare something for us to introduce this very interesting topic. And so what you bring here, what you are going to talk about?
Sure, I'll let you share the slides I'm going to show you. Definitely 2D printing is, two-dimension printing is middle age for us. So today we are talking about 3D printing, but what is 3D printing? 3D printing is an additive manufacturing technology. So basically in opposition with subtractive manufacturing, that is sculpting object from a block, additive manufacturing is creating objects from scratch. So as an analogy, I just put you what could be subtractive manufacturing. So it would be a sculpture from a block of marble. And additive manufacturing will be an igloo made with snow piled up together. So how does it work concretely 3D printing? What we have is first we create the model in 3D dimension on your computer. Wherever your imagination will lead you to. Second, after that, we translate the model into comprehensible language for the machine. So basically, the software will divide the model into slices that will be created one after each other. But I'm going to talk to you about that later. And then finally, the machine prints. It will selectively put matter on each defined zone to print the object. Okay. So when do you think, Michele, 3D printing has been invented?
Oh, wow. I know this is that kind of question that has a crazy reply. I don't know.
For once, it is not ancient Greece.
Okay. But I have still 3,000 years to cover. I would say that, I don't know, beginning of 19th centuries, 20th centuries, I don't know.
No. It's way more recent. Actually, 3D
Okay.
printing, yes. 3D printing, the three most used technologies of 3D printing have been invented in the 80s, actually.
Wow.
So it began in the very beginning of the 90s in 1981, where Hideo Kodama invented stereolithography apparatus, or at least the basic of it. That is a technology allowing how would you call it, photoactivatable, like a resin to dry with some light. So basically what he said is like, I'm going to put some light at some points of my object, and then I'm going to overflow my object with some resin. And so we can go layer by layer to create a full object in 3 dimensions. So it created like, and then this was retaken in 1984 by Charles Hulse, that is the creator of 3D Systems, big company now. So yeah, basically you have a resin and a UV light, a resin in a bath that is, the UV light is curing selectively the resin, and then you go to the next layer. The first functional machine was actually born in 1986. There is a second technology that went just after that. It was selective laser sintering. So this one consists on melting a bath of powder with a laser beam, so infrared light. So it can be, or now it can be metal, but it also can be polymer, plastic, that is like in powder. And the first machine of this one has been created in 1992. And the last one that is the most used by the makers is the fused deposit modeling, so FDM. It was invented in the late 80s and patented in the 1992 by Stratasys. So it consists of a chamber melting a thermoplastic and just filament, and then just depositing the film on a flat surface through a small nozzle. And so now this is the most affordable, the most secure as well, and the most preferred solution for the makers. As well, I didn't talk to you, I didn't put any image on this one, but in 2005, there was a crazy project that emerged. There was the RepRap project. So it was an open source project aiming to create a 3D printer that is able to build itself, or at least to print.
Oh wow, that's cool.
Yeah, at least to print most of its parts. So yeah, the printer in 2008, this printer was actually able to reproduce itself.
Wow. That's cool and a bit scary, I would say.
Yeah, any analogy to Robocop is nothing.
No, it's nothing. It's nothing. So Skynet is not coming.
After
no, please go on.
After the patent on fused deposit FDM expired and fell into the public domain, it was in 2009. And with this RepRap project, 3D printing has seen strong enthusiasm and ramped up rapidly as the cost of machine went down as well. The technique is allowing a lot of freedom when you imagine what you want to create, because you're all doing it from scratch. And it allows to manufacture shapes that are nearly impossible to do with conventional manufacturing. This is a reason why 3D printing is very renowned and growing these days, especially in the maker movements, as I told you. And for example, it allows now to have many different materials printed. So here you can see that there's a whole car that has been printed, 3D printed. There's a violin that has been created, a cast when you break your arm, and even houses in concrete. So metal is part of it. There's a lot of or things we can print now. But what we are talking about today is how to print your organs.
Yeah, exactly. That is something even crazier. And if you are finished with your presentation, we can maybe. Perfect. Thank you so much, Michael. And this was just a small introduction for everybody to try to understand, to put our mind in the setting to understand what our guest is going to show us. So he's a professor in KU Leuven, and he works in laboratory of bioengineering and morphogenesis of KU Leuven. His name is Adrian Ranga, and please, guys, I enjoy you to push you to do a round of applause from your chair, from your couch for Adrian. Hi, Adrian. Welcome.
Hi there. Hi, I'm Michaela and Michael. Thanks for having me on Couch of Science. It's really
doing well.
Really great to be here.
It's very nice to see you, and thank you so much for joining us. Even though it's still a bit warm and there is a bit of sun outside, but still, we want to talk about this, and we found this moment. And thank you so much for being here.
Here, my pleasure.
And I don't want to take more time about for myself, and I will just ask you to. You want to talk about yourself before to start? So what you're doing, where are you from, and all this stuff will be interesting to understand before to start.
Sure, I can. Yeah, I'll give you a very quick bio sketch. So again, I'm super happy to be here on Couch of Science. I guess a few years ago, I was in the U.S. and I had the opportunity to do a Pint of Science in a bar. So that was very very interesting. And now I guess 5 years later, I'm very happy to be back on the Pint of Science circuit. So yeah, a bit about myself. I've been very bi-coastal. So I was born in Romania. I grew up in Montreal in Canada. I did my bachelor's and master's in mechanical engineering at McGill University in Montreal. I then went over to do a PhD in Switzerland at EPFL in Lausanne. And then I moved back to the other coast to the US. I was at Harvard Medical School to do a very short postdoc, and moved perhaps for the final time, at least permanently, to KU Leuven to start a lab there. So I'm in the Department of Mechanical Engineering. So of course, what the idea is really to develop new technologies to do biofabrication. So what does that mean? That means that what we're interested in is to think about biology, actually. Think about how biology uses technology or techniques, strategies to build up tissues, and to think about ways that we can actually build, get inspired by that and build tissues in the lab, which is still, despite having, despite this field being, I don't know if I can say mature, but it's been a few decades now that people are thinking about how to create tissues, living tissues in the lab. We've still got quite a ways to go. So now we're a team of seven people, more or less, PhD students, postdocs, and we have master students coming in as well. So yeah, I mean, I guess that's sort of the bio in short. and then, you know, I'd be happy to also show you some pictures, because that's just a lot of words, right? I guess you want to see.
Yeah, but it's fascinating to know that actually you travel a lot, and your education is also very heterogeneous. So it's something that I would like to go back after your presentation, because I think it's a very interesting point.
Yeah.
And so I will just put your screen on, so you can prepare your presentation if you want.
Yeah.
And in this way, we will be able to see your slides. Here we go.
All right. You can see it?
Yes.
Okay.
Yes.
All right.
So, Adrian, we leave you the stage, and go on.
All right. Sounds good. Yeah. So so really, indeed, we're talking about printing, and so we're talking about how we can. What I want to tell you about is how we use some printing techniques, a couple of printing techniques that I want to share with you, to do a very, maybe a more specific thing, which has to do with printing vessels, printing vasculature in tissues. So we'll get to that in a moment. But what I want to start with is this image. So first, I think it was very interesting, the introduction that Michele was giving, in terms of where we're at with, let's say, non-living bioprinting, and I think that's quite far, right? We can have a printer, we can design a part, download that part, print it directly in plastic, even in now in different kinds of plastic, different kinds of metals, and so back in the late 90s, early 2000s, people really had this thought that it would be, we could do that with body parts. Why not, right? So this is an artist's rendition. Let me get my pointer here. So this is an artist's rendition of how that would work, right? It looks pretty cool, right? You would if you wanted to make a heart, you would design your heart just like you would, a little plastic nut or bolt that you'd want to print. So you design your heart, you put in the right mix of cells into your cartridge, you press print, and then in a few hours, perhaps even a few minutes, you'd have a fully functional heart coming out. So that was 20 years ago, and we're, I guess that was the promise, and we don't have that yet, right? So I'm as disappointed as everyone else, that we haven't managed to make this a reality, this vision a reality. And so the question is, maybe the more interesting question is, well, why not? And is this realistic to do? And I guess one answer is no. This is maybe not the right way to do it. And why is that? Why wouldn't this be an optimal, or why wouldn't this be a good idea? Why would this possibly not work? Or why do we have to do quite a lot more until we get to the point where this could be realistic? And there's a few reasons for that. So I think the driving reason here is about information content. So we don't know the position, the information, the model that we have to input so that we can get all of this, let's say heart, in this case, this whole organ, printed out there. We just don't have that level of detail of information. Where is each cell positioned? We just don't know that. Another thing is that these, even with technological improvements, our printers, our bioprinters, are simply not at that level of accuracy. So even if we did have that information, which we don't, our printers aren't really that accurate yet to position each cell. Maybe an equally important point is that organs are composed of, are not just composed of cells, abstract cells, but cells are communicating. They're organized into, they're linked together. And so if you're going to just print, you lose those connections between cells. So they would be in a particular position, but they wouldn't be connected. So that's another important limitation with this kind of approach. And finally, of course, all of this is connected. It's linked to other parts, to the rest of the body. And so sometimes, you would actually want to incorporate that communication in this kind of system. So we're really so this is really sort of a bit of a fantasy of we can print organs, right? There's a lot of challenges still to get to this point, and I would also argue that maybe that's not the ideal strategy. So all right, so I'm saying this is not, pressing print and getting an organ is not really the right way to do it. What would be a better way? Well, so let's think about how organs develop, right? How do we end up all having the same organs, more or less? Well, that comes from embryonic development, right? So cells know how to assemble themselves, how to grow and assemble themselves into an organ. And so this is sort of a different strategy to start thinking about the biology that leads to organized structures, organized tissues, and try to learn some of those lessons and start to build on that. So it's sort of, if you think about this 3D bioprinting as a top-down approach, what we're thinking about is rather a bottom-up approach. Let's think about what a single cell or just a few cells can do and how we could think about guiding them, mimicking to some extent embryonic development. So how do we start to do that? Well, we need matter. We need to work with some material there, and an ideal material to do that are stem cells. So we're going to take a little detour into biology here, okay? Because it's very important to understand the what the biology is that we're trying to work with here. And so very simply, the very simple definition of a stem cell is simply a cell that can make more of itself, and that can also differentiate, so can turn into different types of specialized cells, neurons or hepatocytes, liver cells, beta cells, so insulin-producing cells. So basically, we like to think about harnessing the power of a single cell to grow more of itself, of stem cells to grow more of themselves, and then to organize themselves into more complex structures. And so in the last 10 years or so, this field has really grown. And so the idea is that, so about 15 years ago, people had this thought that if you put together cells and just gave them some minimal cues, just minimal messages, typically some chemicals, some growth factors that are involved in early embryonic development, then these cells could grow and organize themselves into some structures that begin to resemble tissues, basically simple parts of a tissue. And so these are called organoids. So they're basically miniaturized and simplified versions of an organoid, and they're produced in the lab. They are fundamentally three-dimensional, right? So they often need a matrix around them, so they need some sort of gel support around them. And the really cool thing about them is that they begin to recreate some of the microanatomy of tissues. And so today we have a variety of these mini organs. So here on the bottom, you see one of the most famous examples that was actually in the news when it came out in 2013. So this is a mini brain. And so basically you see here, these colors indicate different identities of different cellular identities. And you see that there's a mix of cell identities, but more importantly, it's not just a random mix. there's actually different structures that appear, that begin to look like brains. They're certainly not brains, but they are beginning to have some of the structure of brains. And more recently, in the last year or couple of years, we've seen that these brain structures, these mini brain structures, also have electrical activity, have some neurons that are the right type, and so there's some organized structure there. And here we see other examples. These are mini guts, optic cups, spinal cord, and some other sort of early embryonic structures called gastroloids. So I want to just show you some of the work that we've done in the lab, just to give you a bit of a feel for these organoids. What do they look like? How do they start? And so basically, you start with these pluripotent stem cells. So these stem cells that can become any kind of cell. Okay, and so if you put together 4 or 5 of these cells, 10 of these cells together, what you see here in blue is the DNA, and so that indicates each of these dots is one cell. You see that if you put them together, they already organize in a very rudimentary fashion, very simple sphere-like structure. Okay, and then this is maybe 10 cells, this is maybe 20 cells, and they've organized there. So there's already they already know, as it were, they already communicate with their neighbors and end up making a very basic structure. And just to give you a feeling for what kind of size this is, so this is a human hair, about 100 micrometers, 200 micrometers in diameter. And so this is the starting point. So if you start with this little ball of human pluripotent stem cell aggregates, it's about the size of a hair. And so if you grow them in the lab, in a culture medium, so in a liquid that gives them just a few pieces of information in the form of chemical signals. So in our case, we've gone towards organoids that are early forms of muscle and vertebrae. And so this is what you get after about 8 days. These are 2 examples. Again, on the left here, you see this organoid that has multiple cells, that is now about 1 millimeter or 2 millimeters. These are all individual cells here. All these little dots are individual cells. And on the right, you see this same kind of organoid that is stained, so that has basically in color the identities, the cellular identities that confirm to us that they are indeed precursors, early forms of muscle. So I want to show you a little video which actually takes us from more or less from here to here. Okay, so this is what we call a time lapse. So we put these cells under the microscope, and we keep recording continuously over 8 days. So what you see here is this 8-day process. So on the left, you see what we call bright field images. Okay, so this is just normal light, and on the right, you see fluorescence, and that basically gives you information on a particular identity. So a very early marker, marker of muscle. So basically, if you see the color come up, that means that particular fate, that particular identity, these cells have become that identity. And so, I'm going to run it again. So you see that that you start as a sphere, and then cells are kind of organizing. They're moving around. They're trying to do things. They pop into a particular direction, and they go into another, and then you have this sort of elongation. And again, you see that this is not just a ball of cells. There's something in there. There's some structures that begin to form. Okay, and I'll just run it one last time, because I love these movies. It really captures sort of the magic of what we do. If it'll run. All right, so it's running one last time, so you get a feel for this. So again, you see this identity, you start to see this very early precursors of muscle, and then they get restricted to one side of this structure. So there's already organization that happens, and presumably in one side has a particular identity, another one has another side, and later in time they these structures begin to organize. So this is really cool, right? This is interesting. You can start to have, without any printing, no intervention from us, cells that basically grow and organize into some millimeter scale structures, and that begin to have the right identity that we direct it to. But what you do see, though, if you take a look at many of these organoids, is that to some extent they have some organization, but each one of them is a bit unique. They're a bit disorganized, and in time, if you see also the previous movie, they basically stop growing. They don't develop further. And one of the reasons for that, one of the key reasons, there's a few reasons, and we tackle a few of these reasons in the lab, but the one I want to talk about today is that there's no blood vessels in these organoids. There's no vascularization, right? And so you know that in your body, every part of your body, every cell is very close, about 200, 300 micrometers away from a source of nutrient, from a blood vessel, from a small capillary or larger blood vessel that has a dual function. It brings in oxygen and nutrients, and it allows for waste to get evacuated. Okay, and so whenever we have these strategies for organoids, we don't actually have that very important feature, and it's one of the reasons why we think that these organoids are not growing to developing further. So that's really a really important missing component. So we want to actually incorporate those kinds of cells and incorporate that functionality of blood vessels. Okay, we think that's really important to begin to build up larger scale organoids and ultimately tissues. Okay, and so the strategy that we haven't come up with this, so it's sort of a conceptually already has been thought about for the last 10 years or so, is that you have an organoid on a device in the lab, and next to it you have a way to bring or to seed, to put there endothelial cells. So these are cells that form blood vessels, okay, in a simplified manner. And with time, these blood vessels will sprout, so will basically come into contact, will grow towards the organoid and begin to feed it, essentially, and remove waste, right? So that's sort of the conceptual strategy. And so the question is, how do we do that? Well, here's where 3D printing comes in for us. So this is a PhD student in the lab. This is Idris. And what he's doing here is actually printing a microfluidic device. So basically he's doing some printing of a system where we can implement that strategy. So I'll show you in a moment what that printed part looks like. But I just want to bring your attention to the fact that this is the instrument that we're using in the lab. So this is a Formlabs printer that you can actually buy. It's a commercially available printer that, if you're a maker, you probably know already about these printers. It is indeed the same technology, stereolithography, SLA, that Mikhail was showing initially. So these are 3,000, maybe 4,000 euro printers, and then we use special inks that are also available directly from this company. So they're medical device grade inks that we use to build our devices. And so why is that? That's really powerful technology for us, because we can iterate a lot of designs. Okay, so you have an idea, You try it out, it works, it doesn't work, you can do it again. So that's the first thing. Having this kind of printer in our lab is really great, because instead of going to the clean room to do to do very complex manufacturing that could take days or weeks, you can do this in half a day or something like that. So again, you make the part on the computer, you print it, and then you have it. The other thing you can do in this kind of experiments, you always need a lot, you need a lot of parts. You need a lot of iterations. You need to do this a lot of times to show that it works, to test it. And so with these, these are small parts, so we can make a lot of them. So that's very easy. And what is important, and so that's, that's great. At the same time, it makes our lab a little bit messy, as you can see here, but that's okay. That's the price we pay for having the flexibility to do all these prints. What's really important when we work with cells, though, is that we really implemented a lot of protocols to make these parts biocompatible, so that they can actually interact with cells in an okay way. Originally, if you just take these materials, even though they say they are biocompatible, we found that, at least with our cells, they're still causing some toxicity. So we have to develop some ways to wash them very well, and ultimately make them indeed biocompatible. So what does this device look like? So how do we actually get cells to begin, so vasculature to begin to connect with these organoids? So this is the device. This is taken from a microscope, stereo microscope. And so the idea here is that we have the organoid here in a central chamber, and then we have the blood vessel, the vessel related cells. So these are called endothelial cells and parasites in channels, in adjacent channels. And over time, they would grow into or close into the organoid chamber. All right. So this is a fluidic, microfluidic device. So it has to do with basically pumping in these cells and having them interact, and also changing media, so changing the liquid that is in this device, so that cells, the organoids, keep having fresh media as well. So another cool thing with 3D printing is that we can actually, we really build every single part of this in our lab. Every part is customized. So we also build, it's not just the chamber itself where we grow the organoids, but we also print these holders that we can put on the microscope. So people really in my lab have gotten really crazy with building everything around it, the packaging around these microfluidic chips. So how does it work? Well, here's an example. We have this organoid. This happens to be a brain organoid. So we have different model systems. So we have the muscle organoid system that I talked about before, and then we have the brain organoid. And so you see here that indeed, when you begin to take these cells as a bunch, as a little aggregate, and you start to push them towards brain fate, they start to make these neurons in the dish. And at the same time, from the other side, if you put these endothelial cells and parasites in the chip, they actually also go towards the brain organoid and start to form these vessels. Okay, so that's quite exciting. And so you can really have the interaction between, here in green, the brain organoid, and in blue here, the vasculature mix. And you see that they begin to connect together. So this is together. So if we're able to get this brain structure and these blood vessels together, how does that improve our brain organoid growth? Now, this is one strategy. This is one way that we've used 3D printing to make these microfluidic devices. Now, this really implies that the way that I've just spoken about really implies that we have, blood vessel making cells and brain making cells, and then we have them interact. What if we wanted to have a system where we could create synthetic blood vessels? So blood vessels that are made from synthetic materials, not from blood vessel making cells. Okay, so that's a bit more difficult, because that really implies that we need to build very, very, very small capillaries, basically. So what's the smallest blood vessel that interacts with other cells? That begins to be extremely tiny, and that really has to do with capillaries. So we've turned to another technology called two-photon polymerization. So basically, this uses this two-photon printing. So basically, this whole apparatus this whole machine allows you to focus a laser into a very tiny point in space, very tiny voxel. And it allows, indeed, if you have this material that can turn from a liquid to a gel, then using this strategy, you can get a very, very tiny point in space to turn into a gel. And so this is actually Sergey, a postdoc in the lab who's working with this technology. And so basically we call this biosculpting, so freeform architecture with biosculpting. And we use this quite expensive, actually, 3D printer. So this is actually like maybe half €500,000 instrument, and it allows us to do stereolithography, just like a 3D, to some extent, like a 3D printer that you would have at home, but with extreme resolution, with much higher resolution, which we need to print these very tiny structures, very tiny blood vessels. And so the idea here is that we're printing a basket, essentially a basket with a radiator inside. Okay, so these would be the blood vessels, the tiny capillaries, and then we incorporate organoids, we incorporate cells within this structure, and they are fed by these tiny 3D printed capillaries. So really, if you can think about if you have an old house and there's a radiator system that basically brings hot water into your house, that's a bit the idea here. So basically, we're printing this tiny little radiators and incorporating cells around it. The key point there is that the radiators are not made of metal, but they're actually made of gel, and so that allows for nutrients and oxygen to cross this barrier, to cross these vessels. And so again, this is very tiny for now. This is the basket, and then we incorporate this into a 3D printed, using Formlabs, a larger scale 3D printed microfluidic chip. And so all of this is perfused. So we're able to we connect it to a pump, and we can flow liquids through tiny capillary networks. And so when we incorporate here, when we include cells or organoids, we see that over time they grow inside these grids. So they're basically, now we have, let's say, a brain structure, little brain cells that are growing, and that they're growing around these capillary structures that are essentially feeding it with nutrients and oxygen. And we see structures inside, so morphogenesis. We see the emergence of form within these structures. And we're now going towards, so we can use this technology to go a bit larger now. We're starting to build grids that are 3 millimeters cubed. So that's really, it seems very tiny still, but it's still extremely challenging to get to this point and to grow living tissue that is that has this kind of size. And so really, I want to conclude with this idea. If you think back on 3D printing that we talked about before, or in the initial slide, it's still, making large scale tissues remains one of our grand challenges in biology and in engineering. And really, we have to look, I think, I'm an engineer, and I as an engineer, I always look to biology to understand how we can take the lessons from biology. How do cells organize themselves, and what are the few things that we need as engineers, we need to bring to them so that they can self-organize themselves better. So really, I think building large-scale vascularized tissues comes from not a brute force approach, but really by understanding and harnessing how cells self-organize. So we really have to think about what are the minimal things that we need to give them, and then we, of course, what are the technologies that match with that. And so indeed, doing this is really one of our big challenges, and I just want to bring it up because I think it's quite relevant to some of the efforts that we're doing. There's currently a NASA challenge called the Vascular Tissue Challenge, and so what they're so they put out this prize of $500,000 to the first group, the first team, the first lab that can successfully create a 1 centimeter, 10 millimeter cubed piece of living tissue, and they have a bunch of technical criteria that one has to achieve. So I think some of these technologies that I've just shown you really go towards getting closer and closer to that large scale tissue engineering. So with that, I just want to show you the team, and particularly Sergey and Idris, who have been really instrumental in building up these 3D printing technologies. So Idris has been involved in the on-chip angiogenesis, and Sergey in the soft microfluidics. So with that, I'll be happy to answer any of your questions. I will sort of turn off this PowerPoint, and I get back to Mikael and Michele.
Here we go. Yes. Adrian, thank you so much. It was really, really interesting.
I don't know for you, but for me, I was at least no one was seeing me, but I was like, wow.
Yeah. It's very fascinating, actually. It's very interesting and super challenging. And first of all, guys from the audience, if you have a question, just drop in the comments section. We are going to ask as much as we can to Adrian without keeping him here all night. But as always, I don't know if you want to start with some question, Mikael.
Yeah, I had one first question is to know how long do you run your experiments to grow these millimeters organs?
Yeah, to some extent, it depends on which organs we want to work with, and also what is our our scientific question. What do we want to see? If we look at the skeletal muscle, the first example that I showed, those actually run for only 8 days. So within 8 days, you already see the beginnings of muscle. Okay.
Mm-hmm.
And indeed, we could, but we don't so far run it for longer. Typically, it would take maybe 2 or 3 weeks until you would see more mature skeletal muscle. I think what is interesting in these in vitro cultures is that development is accelerated. So if you think about in vivo development, embryological development, it often takes longer than what we're able to achieve in the lab, which is good. It's a bit of an advantage, and part of it has to do with how we were able to engineer these systems and how we're able to push just the right buttons so that it goes from one step to another, and that's something that we're still looking into. How are these cells changing from one identity to another, and what are the consequences of accelerating this and all that? So that's for muscle. For brain, sometimes we go to 2 weeks, sometimes 3 weeks. We begin to see electrical activity after about a month and a half, 2 months. Yeah.
Okay, that's impressive. But if you want to continue the experiment, would you have still would your stem cell collapse at some point, or would they still be alive and continue growing?
Yeah, that's a good question. So I think, in a way that relates a bit to why we are interested in developing this vasculature. So if you do grow them for a long time, we haven't, but many other groups have grown these brain organoids for hundreds of days, maybe even a year, and they certainly don't grow into like a brain-like structure. They still remain at this very tiny 1 millimeter dimension, and that's indeed because we think really it's because they don't have the structure around them to further develop. So they don't have these, the vasculature and all that to develop. So they're sort of stuck in a way. They may mature. Individual cells may mature further as time progresses. So they don't necessarily collapse. They stay alive, but they stay very small and sort of, yeah. They may develop in terms of identity, but they don't proliferate. They have a problem in proliferating.
Okay, thank you so much, Adrian. Was very clear.
Yeah.
We have a first question from Peter. I don't know.
Yeah.
These baskets are filled with gel vasculature. Do they allow diffusion of molecules such as growth factors excreted from nearby growing organoids? That's a very good question, actually.
Yes. Yeah, that's indeed a very good question. So the whole system is designed in such a way that it's just gel. So all around, so the printed vasculature is gel. The material that surrounds the organoids is also gel. And so these gels by their composition, by definition, allow for diffusion of growth factors, of small molecules, drugs, for example. So I didn't talk about this, but this kind of system we think can also be, I sort of anticipated more towards engineering tissues, but on a shorter term, what these models are very useful for is, for example, for drug testing, for more realistic drug testing. And so indeed, this kind of system allows for diffusion of various molecules. Yeah.
About this, actually, we have another question from Clem. How did you identify the chemicals which are responsible for the differentiation of the cells? I assume they are different from each type of organoids. So we are going deep in embryology right now. So
yeah, exactly. No, that's a great question. And yes, so they are, the first point is that they are indeed different for each type of organoid or each type of tissue that you want to be generating. And that really has to do with long time research that exists already, that has existed for decades. People understanding, or people looking, and again at the embryo, at embryology, and purifying or understanding which factors are secreted by different cells. So originally, this has to do with understanding the biology of embryonic development, and more recently, meaning in the last 30 years, taking those lessons and to some extent by trial and error, but also of course by, let's say, intelligent trial and error, using these factors in the lab in vitro cultures. And so of course, before the advent of these organoids or 3D culture, people were doing 2D differentiation, so cells on a plastic dish. And we've learned a lot from people trying different recipes or different combinations of factors that have led to particular outcomes, so specific outcomes. So people now, for maybe 15 years now, people know exactly the factors and the right timing to put these factors in place, for example, to generate motor neurons. right, to get something very, very specific as an outcome. And so, the whole organoid field gets inspired or uses some of this information, this knowledge, in order to figure out what the right factors are. To some extent, that is known, but to some extent as well, and that's a challenge that we face, is that through biology in 3D, it can be quite different than biology in 2D in vitro. And so sometimes, even though some of the factors and the timings are known or would be known for 2D cultures, when we try those recipes, let's call them recipes or protocols in 3D, we find that things are quite different and we have to tweak them, particularly timing.
Okay. I have a question, actually. You were mentioning before something very interesting. You said that probably these organoids plus this capillarity system, they can become like a kind of a model for an organ. Is this something that might be applied to pharmacological experimentation, for example, to avoid to use animal models or to reduce the number of animal models? Do you think that is something that in the future can be implemented? So try to substitute the use of mouse or part of that with like a fake organ that actually can be injected with the drug?
Yeah. That's an excellent question, and I think all of us who do work in organoids are targeting that. But we also, I think, we're all also very careful to say, look, that won't replace animal testing completely. There's always that step that I think is also necessary. We're building reduced models, simplified models of biology, and I think they're very powerful in that we're able to recreate some of the functional aspects of specific parts of biology. And so, if you're talking about, for example, liver toxicity, well, if we're able to build better models of a human liver, that's one of the big pluses of this kind of in vitro biology. We're able to take human cells and create a structure that begins to have the function of a little piece of a human liver. So that's very powerful. So I think those are big advantages of these in vitro cultures. At the same time, there's a lot of feedback, a lot of immunological complexity, etc., that we're not yet able to model, in that I think there's still a relevance for animal models, and there's still a place for them. But indeed, if we can reduce that to some extent, that's a big plus with this kind of approach. Yeah.
Okay.
Sure.
Thank you so much. It was very, very clear. Very clear, at least to me.
Sure. I'm glad.
To follow up on this question, actually, and the other from Peter, what can be a use for these organs, these organoids, this beginning of a function you're having, except testing drugs, as you said before?
Yeah. Well, I think I'll tell you what. So there's one of the pioneers in our field, Hans Clevers, who's in the Netherlands, has actually built a whole institute that is dedicated to personalized medicine using organoids. And so he's already shown some very interesting examples of taking making a biopsy from a patient and growing their organoids, so growing multiple of their organoids in the lab and treating. So these are rare genetic diseases. So they don't have a lot of information. They don't have a population on which they could test, different kinds of combinations of drugs. So they basically do a personalized drug test on these organoids, and they look at some functional readouts. So in particular, this is I think an intestinal organoid, and they look at whether it expands or doesn't as a function of these cells, these drug treatments. So I think there's really interesting experiments that you can do in vitro. So so that's one aspect. So personalized medicine is one aspect. I think the other thing, fundamentally, we can really learn a lot on the basic science aspect. So this very basic question that we all have: how do a few cells end up communicating with each other and organizing themselves to form such a complex organ that function? All of these cells work together ultimately to do what they're supposed to do, to generate motor function, if we're talking about brain, to ultimately even higher level thinking and cognition and all that. And so we're able to study these processes in vitro. We're able to dissect all of these different influences of the external environment. So we're able to really understand and take apart the complexity of biology, and maybe understand at a deeper level what are the minimal pieces of information that these cells need to build up larger scale structures. I think that's one of the things that really excites me about this kind of systems. And maybe in a longer longer scale of time, we can begin to build up even larger structures for regenerative medicine applications. But that will take a bit of time and certainly a lot of testing and optimization.
Of course, yes.
Still a long way to go, but
Sure.
we will reach that point. So I would do just a very last question, maybe, or maybe a couple. I will go for okay, this one. This one is quite intense, I would say.
Yeah.
Building on the slower development in vivo, do you think the slower development is due to some inhibiting factors which control growth, etc., safeguarding quality of the organ? Do you think this needs to be mimicked in vitro?
Yeah, that's a super interesting question. Yeah, we don't know yet why this happens. I think you may be right, Peter, that things. So the building steps in vivo are extremely tightly regulated. I mean, it's been over millions of years that we've reached a point of, things happen at a particular time for a particular reason in vivo. And indeed, if we don't do it in vitro, that may be the reason that we may have some dysregulations. Indeed, that's right. So I think part of it has to do with the fact that organs are it's never or very rarely just one cell type. So you have multiple cell types, and they all have to come in at the right, they have to emerge, be born at the right time in order for the organization to happen correctly. And so, of course, if you accelerate the process, you may not be able to capture the right sequence of events for the tissue to develop. So indeed, you're right. This may be safeguarding quality. It's like a quality control system. So you're very right. That might be a consequence of accelerated development, and we're looking into that, and we're trying to understand if that is indeed the case, or if we can accelerate the process in a correct manner. That's something that we'll be able to look into. Yep.
Okay, thank you, Adrian. I think we have a very last question, which is I was curious about it as well.
Yeah.
Which one do you think is the easier organ to model?
Yeah, that's a good question. A few very more simple organs have already been tissue engineered. Okay, so for example, the bladder has already, there's been bladder transplants into young children, tissue engineered bladders. why does that work? Because the bladder is a simple non-vascularized organ. So basically, if you grow, you take bladder cells and you have them grow over the right, shape, then that has been successful. That has been a successful project in engineering tissues. The more vascularized, the more cell types are involved, the more complex one would think is the technologies that need to be put into place. Yeah, I can tell you probably the brain is as always one of the grandest challenges, because it has sort of almost unimaginable structure and complexity. So that's always, that's on the other scale. So yeah, I mean, to summarize, some tissues we've already modeled, and as we increase in complexity, I think the challenges will be greater. Yeah, maybe, from our perspective, maybe muscle can be relatively easier because it's more restricted cell types, and the organization is, well, I wouldn't say simple, but at least can be, there's a bit more knowledge, there's a bit more prior knowledge on how to do it.
Okay, perfect. Yeah. I think that we can wrap up. Adrian, thank you so much. It was a very interesting topic. You are you're a great speaker and very prepared. Yeah. And it's always good to have such a prepared guest and passionate, actually, also about the topic. And before we leave, I don't know, Michael, if you want to disclose about the future events that Pint of Science Belgium is putting together.
First of all, I want also to thank Adrian, because it was a great speech. It was very, very interesting. Thank you for coming. We're very glad to host you on this event. And actually, yes, Pint of Science.
I want to say thanks to you guys so much. It's a great opportunity to do this, and I think it's I get very stimulated by your questions and the questions of the audience, because it's usually in a scientific conference you get very specific technical questions, and this really helps to really think more broadly on the topic. So again, thanks for putting this together, guys.
Great.
Thank you so much.
Yes, actually, Pint of Science is back, and with a program that is going to be biased with the current situation in Belgium. But we're going to have a few events. A few are going to be online. So from the 7th to 10th of September, we're going to have events. Stay tuned on the 7th, the 8th, and the 9th. We're going to have online events. And for the 10th of September, we're going to have one presential event in Brussels. So keep being updated. There's going to be a few tickets, so don't miss the chance.
Yeah. We need to keep the physical distance, so we cannot host so much people, basically, and unfortunately. But this is a situation we need to continue to share beer and science as much as we can. And okay, so guys, from the audience, if you have any questions, if you want to ask something else, if you want to collaborate with us, whatever you want to do, just drop us an email. You can follow us on Facebook, on Twitter, on LinkedIn, on Instagram. So on YouTube, we have also a channel on YouTube channel. Some of you is following us right now from there. And I think that's it for tonight. We said everything we had to say. Adrian, again, thank you so much, and good luck with your work. And maybe we will have you for a live event in the future, maybe in Leuven, maybe in Brussels, who knows.
Sounds good. Yeah.
Thank you so much. And thank you so much, guys. I always say thank you also to Anna, Renata, and Matteo in the background. They help us with the technical stuff, the chat and the comments. They always remember us to select the questions and to ask the questions. So it's very good to have them to help us. And for tonight, hey, Hannah here, Matteo and Renata. Here we go. Everybody's on screen. And thank you so much, guys. Have a nice evening and see you soon in September, I guess. And bye-bye.
Bye.
Bye.
Thank you again, Adrian.
Sure, my pleasure.